But moving on rapidly, I see Werner is eager to come to the podium and provide solutions. I twisted Werner's arm very strongly to come here, and he promised he would, and he did. So thank you, Werner. Werner Kutsch is CEO of ICOS, the Integrated Carbon Observing System, and I'll let you speak on how our observations are going to help us out.
Yes, thank you very much for having me here. And I was thinking during the day that this presentation is even unnecessary because observations were so many times mentioned by Rona, by Pierre, and by many others as input into inverse modeling and so on and so on. So I want to try to be short, which is difficult for me usually, and would like to concentrate on three main potential of in-situ observations. No, oh yes. And the first one is climate carbon feedbacks, many times mentioned in many questions. Maria asked, will the lens sinks perceive, and so on and so on. So the impact of climate change on natural processes, in particular the natural carbon cycle, is a major concern of climate scientists. And there are many things that can happen: droughts, temperature effects, thawing, fires, but also CO2 fertilization, greening. And the research infrastructure observing the carbon cycle is really pivotal for understanding these carbon climate feedbacks. And I will give a few examples. Important is that we are, just to recall this, talking about these important ocean and land sinks. And recently, if you have followed the media, there are this alarming news that the land sink is completely broken, and so on and so on. And I will briefly cite this paper by Key et al. That was recently published, which is showing that in 2023 the land sink was almost completely breaking down. Interestingly, they used only a small sample of fast-track models. They were using only satellite data, and what I read really with interest was the reason why they used only satellite data was while most of in-situ surface network measurements are not yet available. And that's interesting for me because we made an intervention at the last COP showing 30 sites from ICOS until November last year, and showing already the increase during the year 2023. So it's simply not true that in-situ data are not available. But there's always potential for improvement, and this is a analysis that we made in one of the EU projects. We are coordinating CADI about potential for adding in-situ sites in region with low density of observations. This is a footprint analysis for potential sites in Africa, and you can see on the left-hand side there is the current situation, and on the right-hand side is a more ideal situation, and it's not a big investment putting something like 10 or 12 more stations into Africa. And with this CADI project, we are supporting this work. So, a brief summary: climate carbon feedbacks, they are really complex. They need thorough and long-term observations. We need long time series to allow the interpretation of the extreme events, but also the detection of complete changes of the system. And the global spatial coverage, as I just showed, needs to be improved, particularly in areas with frequent cloud coverage. The second potential that observations have is detection of emissions and support of inventories. We heard a lot about this as well. So inventories can be supported by in-situ observations and modeling. There's a high potential, in particular in urban areas. And Frank put the question on me while we were talking before this meeting: have we peaked emissions, and can we see this from in-situ observations? And my answer is yes, we can, but only if we know the natural fluxes better. or we should say, yes, we could. So this is now an example, also of a recent paper, Scapelli et al., which compares satellite-based observations and in-situ observations, mainly from the ICOS network. And they were using this as for an inverse modeling. And they had the priors, you can see on the left-hand side, and then different observations with CO2 and CO. And you can see on the top, for several countries, the result for satellite observations, and on the lower part for in situ. And interestingly, they are going, the posterior going into different directions. When you look at Germany, for example, they are decreasing, the satellites are decreasing the emissions, the in situ are slightly increasing the emissions. So there are still some things to learn when you compare this. And they conclude in this paper that OCO2 alone cannot reproduce a posterior European CO2 fluxes, and also that an in situ network is still essential for constraining biogenic fluxes. So what is this in situ network in our case? It's ICOS, the Integrated Carbon Observation System. We have about 180 stations all over Europe. 16 countries are contributing. So we have ocean stations, we have ecosystem stations, we have atmospheric station, which are all served by thematic centers. There is a central analytical lab providing analyzers, but also calibration gases. And all the data are completely open and free and fair at the ICOS Carbon Portal, available for users. And what I also have to say, they are available near real time. So you can get from the Carbon Portal yesterday's CO2 concentrations from more than 30 stations all over Europe. You can see in this picture 3 colors. If you could look at the upper right picture, the light green color are data from ICOS stations before ICOS was existing. The dark green are ICOS data, so it's the so-called level 2 data, high quality data, and the red ones are near real-time data. So every time we release the high quality data, the quality check data, which is the green, the dark green color, we replace the red ones and start a new data set with new near real-time data. So in principle, you can go back to at one stations 20 years, but you can also get yesterday's data. And what I forgot, we have also a lot of ecosystem flux data from almost 100 stations. So why can we support, in particular cities? We have a project, the ICOS Cities, that is specifically looking at the possibilities to support inventories from cities, and this is a result from Paris. And you see different calculations or different data sets, but there is also one that is that is from observations, and you can see this is very nicely supporting the inventories. And while I'm talking about the ICOS Cities project, if you are interested, we have a meeting where we specifically want to connect between scientists and the policymakers in cities in 3 weeks' time in Barcelona. So if you're interested, there is still space for this. The third thing is certification of carbon dioxide removal, also a question that was discussed already. I have a very simple view on this. We had all these complex ideas earlier. I have a very simple view on it. If there is a farmer who wants to gain a certificate, and then this farmer has to change the management, and he has or she has to be connected to a broker who quantifies the effect and provides the certificate, and then goes to the market. And however you call it, you need something that is a catalog of removal practices. It could be done by the IPCC, or it could be done by GRC or whomever, saying, okay, this practice on this soil, in this farm with this history, generates a certificate of X tons of CO2. And this catalog needs experiments, process observation, long-term observation. So that's the place where observations can also feed into this carbon dioxide removal certification. And of course, monitoring is a big issue, and the monitoring itself will also, of course, give information into this catalog. If you want to learn more, we have an annual bulletin, and this time it's on monitoring, reporting, and verification of emissions. And my colleague has some exemplaries there if you want to see it. So, summarizing, the three most important potentials of in-situ observations are understanding and quantifying carbon-climate feedbacks, supporting and verifying inventories, and also long-term observations for CDR certificates. And I think that's it. Thank you for your attention.
Thank you, Werner. Please just take a seat. Bram, please come up now. Bram's, I will not pronounce your name properly, so it's Maasakkers. I'll ask you to pronounce your name. Bram is working with SRON, the Netherlands Institute for Space Research, and he's doing some very interesting work in actually looking at methane hotspots, tracking them down and shutting them down. So, Bram, please.
Can we go to the first slide? Thanks. I do hear myself, but that may be okay. I hear myself quite a bit, but maybe that's okay. As long as you guys will hear me. All right, yeah, so I'm Bram Maasakkers. I'm a senior scientist at the SRON Netherlands Institute for Space Research. And in addition to the in-situ perspective, I'll add a perspective from space. So using satellites, we can estimate emissions, but I'll mainly focus on another use case, which is supporting mitigation efforts. And that is especially important because well, that was nice, but we'll skip it now. That's especially important because we know that when it comes to methane, we have these super emitters, sites that emit much more than similar sites and emit in large quantities. An example is shown here in the Permian in the United States, where the New York Times took infrared footage of a tank which was just leaking gas into the atmosphere. Now, if we know where those big emitters are, we can target some of our mitigation efforts on them. However, for a gas that's odorless and invisible, it's hard to figure out which are the sites that we need to focus on. And that is where we can help from space. That's not going to get us to the goals of the Global Methane Pledge, but we can at least make sure that we're starting to get rid of these really big emitters. So how does that work? Observing methane from space works by looking at reflected sunlight. So the light comes from the sun, it goes through the atmosphere, it's reflected by the surface, and then it goes up to the satellite. And along that light path, light at specific wavelengths gets absorbed by methane molecules. But on looking at how much light has been taken away, we can estimate how much methane is present in the atmosphere at that location. And one of the key satellites that we're using for that is the Tropomi instrument on ESA's Sentinel-5P satellite. And you can see an animation of that satellite on the right, where you can see that it circles around the Earth, and that way it's able to observe every location on Earth every single day. So we get another snapshot day after day after day. And the individual observations that it produced cover an area of about 7 by 5.5 kilometers. And that allows us not just to evaluate emissions over large areas, but also detect large individual methane plumes. So here I'm showing an example of a gas well in Louisiana in the United States that exploded a couple of years ago. And on the left, you see drone footage, and you see that from two of the wells, the gas is just blowing into the atmosphere. Now, in the video, there's still some combustion, but later on during the event, all of the gas was just going into the atmosphere without burning at all. And that is when we took an observation with Tropomi. So here on the right, these individual rectangles are our observations. And the more red they are, the more methane is there in the atmosphere. And you can see a plume coming from the X, which is the site of the accident, moving all the way to the northeast. And when we quantified this plume, we quantified it at about 100 tons an hour. So to put that in perspective, that's 3 times as much as the rate of all anthropogenic methane emissions from Belgium combined, all in one single spot. So that really shows you that these are the plumes that we at least want to focus some of our mitigation efforts on. However, we take millions of observations, so we don't want to go through all of those data by hand. And that is why we developed a machine learning approach to automatically detect these plumes in the tropomi data. And this is an overview of what we detected last year. Now here, we're detecting plumes every day, so persistent sources will show up multiple times. But also there are a lot of emissions that would go below what we would see as a big plume in tropomi. So if there's no circle, it certainly doesn't mean there are no emissions, just means that there wasn't a plume that was detected with this satellite. So we see a mix of sources going from coal mining emissions in Australia as well as China to large cities in places like India, where we, for example, have waste emissions. Then we see the oil and gas infrastructure in Russia, Algeria, as well as in the United States, for example, in the Permian. Now, with tropomi alone, it can be hard to pinpoint what exactly it is that is emitting, because if your observation is covering an area of 7 by 5.5 kilometers, there can be multiple facilities within a single observation. And that is why we combine tropomi with a number of high-resolution instruments. The most prominent one so far has been GHGSat, which is an instrument by a Canadian company that can observe methane at a resolution of 25 meters, but can only do so for limited domains of 10 by 15 kilometers. So they kind of need to know where to look, and that's exactly the information we can provide based on tropomi. And recently, we've also expanded this to use satellite instruments that weren't really designed to observe methane, but can still detect the largest methane plumes. So here, for zooming into Buenos Aires, on the left we have a tropomi average over a 2-year period, where you see these enhanced methane concentrations over the urban area of Buenos Aires. And then with GHGSat, we zoom in to the box that you see, and we get the image that you see on the right, where in the center of the image we see a large landfill that, for this particular GHGSat observation, is emitting at a rate of 20 tons an hour. So this is really one of the biggest emitters when it comes to landfills that we've seen, but we've now spotted these landfills really around the world, including in Europe. So show an example of one of these satellites that weren't really designed to observe methane. Here, in the background, we have our tropomi observation, and then we zoom in with Sentinel-2. So Sentinel-2 is originally a mission that's designed to observe the surface of the Earth. But because these methane emissions are so big, we can still get some signal out of the data. And here we find emissions from 3 different oil and gas facilities, where one of them, if we could look back at the Sentinel-2 record, has actually been emitting for years. So it's really a mix of persistent emitters and also more transient ones. So we now do this detection of plumes on a weekly basis for a CAM service. And this is the map from last week. So you see that a lot of those locations are still active. And so behind every single one of these circles is one of these tropomi plumes. So just showing an example of the week before, this is a plume that we detected over Kazakhstan. This is a really big plume that we could again pinpoint with Sentinel-2 to be coming from an oil and gas facility. And here it's emitting at hundreds of tons an hour. Now, the next day, it's not doing that. So we really see a mix of the persistent emissions and also very short duration events, for example, venting from compressor stations, where you get these really big plumes, where having the additional observations from these instruments that weren't designed to observe methane really helps you in what you can pinpoint. Now, of course, we don't just want to stop at detecting something. We also want those emissions to be mitigated. And that is why we provide our analysis, for example, what we do on tropomi, to IMEO, the International Methane Emissions Observatory. So they operate under the flag of the UN, and they have this methane alert and response system that was briefly mentioned before. So the idea is that we provide our analysis, and then they form the bridge to the responsible governments and companies to then hope to get persistent emissions mitigated, or inform them that some of the procedures that they're using are producing these transient emissions. We also see that in some countries, there are now specific super emitter programs that are also using this type of data, for example, in the United States. In addition to that, we are evaluating how we can use these data to support emission mitigation at landfills. Now, for landfills with gas capture systems, you may have something that's more like an oil and gas leak. But we're also evaluating how we can use this in the Global South to work together with local parties to use these observations of methane to mitigate emissions from these big waste dumps that often come with a lot of additional issues, such as air quality or water pollution. And this is a project that we're doing with the Global Methane Hub, and also supports the Lowering Organic Waste Initiative that was started by the State Department in the United States, and also includes European contributions to also try to unlock funding for these kind of sites, where mitigating emissions can go hand in hand with improving living conditions for local populations. So when it comes to observing methane, which is what I focused on from space, we're really only at the start. This year already, we've seen launches from additional instruments such as MethaneSat and Carbon Mapper that will help us to even detect more plumes and also some of the smaller plumes. Hopefully, by then using this data to support mitigation efforts, at some point we'll also start to see fewer plumes and our maps will start to clear up. Thank you.
Okay, thank you, Bram. Just sit down here for a moment. We have about 2 or 3 minutes left for questions. Is there any immediate questions from the floor about, obviously, I asked you here because it's important that we do realize the potential of these technologies. And I think if we can get the methane capacity and chase down methane, as we heard earlier, we have a great potential for doing something rapidly on climate. So, Sally, I see your hand up there.
Thank you. Sally Stevens from the Magical Project.
I forgot the basics.
There you go. Sally Stevens from the Magica Project and from University of Reading. A comment really. I think there's some really exciting upcoming satellite launches that are collaborations led by the European Space Agency, which will really increase capacity to use Earth observation for these monitoring methods. And I'm thinking particularly of biomass, which was mentioned earlier, the challenges of identifying that, not just the health of trees from above, but the issues of degradation and future health below the leaf canopy, but also microcarb. Both of these are going to be launching next year, and microcarb will have a specific city mode. So that will really help with emissions. And I think your mention of GHGSat, for example, is fantastic, because that's a really inspiring example of a commercial company working with governments to address these important policy issues and find the solutions.
Thank you, Sally. I don't think there was a question there. I think it's support. What I'll do is I'll ask Werner and Brahms, if your next steps, where are you going next in terms of in-situ observations? Obviously, you highlighted Africa and your collaboration with WMO. So, and then
well, we have one exciting next step, and that's hopefully integrating the TCON network into ICOS, which would enable us to get much closer to the satellite community, because TCON is in principle the same technology just looking up from a certain point into the sun. And this would be helping to calibrate the satellites and bring these two communities closer together. As I already mentioned, cities are one point where we would like to extend. We are developing the methods for that, and so on and so on. So we have ideas to develop further, which we are intensively also discussing with the potential users of this data, which is important. We don't want to satisfy only our curiosity. We want to serve the community.
Yes, I think there are two sides to it. One is improving our analyses to be able to detect more, automate the processes so we can automatically scan through more data. And then it's working with stakeholders not only to optimally use these observations to reduce emissions, but also, for example, analyze how we can best incorporate them in emission inventories.
Great. Great. Oh, Maria, you wanted a quick question?
I would like to congratulate you because indeed early warning is fundamental to address big sources. And I think what is being done already by ICOS and also by what you saw, Bram, it is extremely useful for governments to focus on where large emissions are happening. So I think it is very nice that you will continue to enhance the absolute numbers that are produced and the small sources and so on. But what you are providing now is fundamental already. And I think we have to put value on that fact rather than trying to refine. You can keep refining, it's not a problem, but let's put value on what you already achieved. And I think, ICOS, which I know because I was starting ICOS in Spain, ICOS already provided a very fundamental understanding on how Mediterranean ecosystems are behaving and reacting to certain events. And for us, this was fundamental to understand how better to manage them. So I think this is the value of the systematic observation. And for satellites, we should already start using this data to actually identify where the hotspots are. I think that's fundamental. Also for health of ecosystems, for example, is fundamental, because if I suspect that my ecosystem is not going well, then I can start acting. While if I rely only on my forest inventory, I may need to wait for too long. So I think this is a very important function of what you have been describing today.
Thank you, Maria. And what I would say as well, obviously, if we can point out these leaks to those responsible for those leaks, then they have a responsibility to act. So with that, I'd like to bring today's meeting to a close. It's been a long day, no doubt about it, but it's also been excellent as far as I'm concerned. I really appreciate all of the material that we heard here today. And I wanted to point out that at the front there's a whole list of those pages which gives you the indicative messages. We'll be refining those in the coming few days, so your feedback on anything will be really valuable. But with that, I think let's go and discuss this further at the reception outside the door. And we start again. Petra, I'll hand it back to Petra to give.
Yeah, just thanks a lot. Thanks, applause to the speakers and to the chair for this session. Very interesting final session of the day. Yes.